Greetings everyone, my name is Treasure. We are here at FESTO today. So for today's lesson, we're going to be looking at PLC programs and loading that PLC program into a real PLC and controlling a real hardware with that program. But before we get started, I'd like to answer some questions from the previous lesson that we did on codices. Now, there was a question about the PLC itself to say, where is the PLC in the program that we used there? So codices has an internal PLC, it has internal PLC, PLC sim, which is called Control Win version 3. So this is where the program went. When we logged in online, we downloaded the program, it went into an internal, let us say, simulation PLC in the computer itself. And this PLC is capable of controlling the virtual IOs, so that when we were actuating a 1M1, these are happening within the internal PLC of the device. Without wasting any time, we are going to start with today's lesson. So today's lesson is basically about MATLAB, a MATLAB conveyor. MATLAB conveyor consists of a conveyor belt, which is here. This is where the parts are going to move. It also consists of a plunger. This is it here. Sometimes it's called a sorting gate or solenoid. This is a solenoid actuator. So when solenoid is on, workpiece falls into the slide. But when solenoid is off, workpiece is able to actually pass through the conveyor all the way to the end. Okay. And there's also different sensors. So we have optical sensor. This is the one here. There is also an inductive sensor, which is this one over here. What inductive sensor does is it detects any metallic parts that are passing through the conveyor, while the optical sensor uses a transmitter and receiver. So there's a transmitter and a receiver here. Light is transmitted here and it's received there, so that if there's any object in between, it blocks the light beam, and so this is where we get the signal from the sensor. To make controlling the conveyor simple, we are using a motor controller here, which consists of two relays so that we can control the motor in both directions, forward and reverse. There's also an I/O hub here. This allows us to connect M8 socket of the different sensors and actuators. We also have a PLC that I've shown last time. This is the CECCLK PLC. It has 14 inputs and 8 outputs. And those are accessible via a connection here. This is syslink connection. I'm going to plug it onto the PLC. The other end, I will plug it onto the MATLAB conveyor. Now, I've connected the PLC to the MATLAB. Now the PLC, I program it via Ethernet cable. This is plugged onto the PLC, and the other end, I'm going to plug it onto my computer. Right. Now, once this is plugged, you need to make sure that the IP address of the computer and the IP address of the PLC are correct. And such a way would be that we scan FESTO devices in codices, and you can see that I'm finding a device, and the IP address of the device is 192.168.0.1. Now, my PC or my computer has to also have an IP address of 192.168.0, but the last digit should be different. It can be 2 or any other number ranging between 0 to 255, of course, except for 1. There's also a thing called subnet mask. Subnet mask is like grouping of different devices in a network. Subnet mask for the computer and the PLC have to be identical. You can see that the PLC has a subnet mask of 255.255.0.0, and the computer needs to also have similar subnet mask. Let us see. Now we can see that the PLC, the computer IP address and the computer subnet mask are correct, which means that we will be able to establish communication with the PLC. So we switch to codices, and we go to create new project here. When creating a new project, as I said with the previous lesson, that you should select standard project. This is when you are not using real hardware. Now that we will be using a real PLC, we must select the PLC, we must select a template with the correct PLC here, or correct controller. In this case, CECC project. And it asks us whether we want to save the previously open project. You can say yes, or you can say no. It's entirely up to you there. So now, selecting the device. So CECC comes in 3 variations. We have D, S, and LK. So for this, we are having LK, so we will select LK. Now, it also comes to PLC Programming Language. So previously, we've done structured text and sequential function chart. So let me show you ladder. We're going to start with ladder this time. Okay, so now, what is very important when creating, when studying your coding, is to know the different sensors, the addresses of the different sensors and addresses of the different actuators. And for us to know this, we need to go to onboard IOs, onboard digital inputs. We go to variables. We can open this up, and then we need to select enable to. This will allow the codices to read the inputs even when they're not used in the project. Otherwise, it will not read them. We do the same thing with the outputs, because we first want to identify which addresses the different sensors and different actuators are. After this, we go to device. We need to scan devices, and you can see that I find, so you double click, or you can highlight gateway, and then you scan network, and you will see that the PLC appears there. If I had multiple of PLCs, I will see multiple of PLCs here. So because I have only one plugged, I'll set it as an active device or active path, and then I can log in. After this, you need to start your program. Let us go to the inputs. You can see that at this point, everything is false. And if I put a part in front of the optical sensor, you can see that one input turns on, and this is bit 1, and this is the address. We need to remember this address. You will see why. And then let us see the inductive sensor. So inductive sensor, you will see it's 0. So 0 and bit 0 and bit 1. All right? Now we go to outputs. We need to see, if I turn on the first output, what happens on the station. So to turn on an output, you need to go to prepared value. You need to specify the state which you need. In this case, I need it to be true, so I will make it true, and I'll press Control in together with F7. And you can see that the plunger turns on, so I know that 0 is the plunger. Let us see what about bit 1. You can see that the conveyor runs. So bit number 1 controls the conveyor belt direction forward. Now that we have identified the addresses, we are going to go to the PLC program. In the PLC program, we have to go offline because now we need to put in information. So we've first identified the inputs. So / is actually a comment. So I'm going to have to start with inputs, and then I have OPT, actually IND, which stands for inductive sensor. This is at %IX 0.0. And we put colon to specify what type of a variable this is. So this is a Boolean, all right? And then the second, we have seen that it was optical sensor. So optical sensor, it's at %IX 0.1. This is also a Boolean. So we have different data types. We have Boolean, we have word, we have real, we have integer. They are all different. Boolean is a data type for a bit. Now we come to the outputs. So outputs, we have seen that the first was the plunger. So I'm going to say plunger here, or one can also say K1 or use shorter terms, because when you're writing the code, you don't want to spend too much time typing the words. So using short words is actually quite a good thing. So we will say K1, which we know will be the plunger. And we know that this is at percentage QX 0.0. And also this is a Boolean. Now I can write a comment here to say K1 is a sorting plunger. We have M1, which is the conveyor belt, which is at QX 0.1, the first address there. So this is a Boolean. I can also write a comment and say conveyor forward. Forward. I can do the same thing with the inputs, just so that we can remember what they are. So this is optical sensor. And this is inductive sensor. Okay. Now we are ready to start the program. At this point, we can add a new rung. The first thing on the conveyor is that the optical sensor detects the part. Only when the part is detected by the optical sensor, the conveyor should run. Otherwise, the conveyor shouldn't run because there's nothing to transport. So we need to start with that. So our command will start with an input, which will be optical. What does optical do? Optical turns on M1. Now, this will mean that the conveyor will run. However, immediately when optical turns off, conveyor will also turn off, and this is not what we want. We want the conveyor to remain running up until the material is transported all the way either into the slide or to the end of the conveyor. So for us to be able to have it running even after optical sensor has turned off, we use a function block, which you may be very well familiar with, which is a timer. T-off, which delays the off state of a variable, in this case the conveyor. And by just looking at it, we can actually check by using this manual override here. We need to sort of time it to be able to determine how much time does the conveyor need to transport a part from the start to the end. So I'm going to start in my head the timing. So we have 1, 2, 3, 4, about 4 seconds. Just to be on the safe side, we'll make it 5 seconds. So we add a function block in between the input and the output. This is T-off, and T-off must be given a name. So we will give it 0, T-off 0. ET is the display of the timer. At this point, we won't go into depth about ET, but PT is what's important. PT is the time itself, and we denote time by T hash 5S. So T hash is basically the time. It's time. 5 is number, and S is second. So we can say M for minutes, H for hours. We will use seconds for now. So now we can see that optical sensor will detect a part. It will turn on M1. M1 will remain on up until 5 seconds, up until the timer has reached 0, from 5 to 0 seconds. The second thing that happens is that the inductive sensor will detect a metallic part. And when it detects the metallic part, we need to turn on the plunger so that the material can go into the slide. So meaning that this must also remain on even after the part has gone past the inductive sensor. So just looking at it, it's about 2 to 3 seconds. We will start with 2 seconds. So we add a new rung, and this is inductive. And this is K1. We put in a timer also there. So this is going to be T of 1, because timers cannot have the same name. If they have the same name, they are one thing. And these are not one thing, they're doing different things altogether. So we have said that we're going to say T hash. We said 2 seconds should be enough, hopefully. If it's not, we will increase it. So the coding is done. Now we're going to load this program and see what happens. We'll run the program, put a part, turns off. Let's put this one here. Conveyor stops, voila. Now we come to the control part of it. You can see at this point in time, the operator stands in front of the machine and they have no way of controlling the machine. I cannot stop, I cannot start, I cannot reset the system. So this is what we're going to do next. So we're going to use a visualization in Codesys. So we go to Add Object, we add visualization. With visualization, there's a toolbox, visualization toolbox. So I'm going to bring in buttons. So this is, I can give it a name, text. So I'm going to name it Start, so that if I press the Start, then I can start the system. And I will have a Stop. And I will have automatic, excuse me, this should be reset, because automatic we use a toggle switch. Should be here. And for this one, we need to bring in a text box here. And then we can label it automatic manual. Just need to move it in place right here. Okay, so now we need to come to the variables in our PLC program, and we have seen that the first set of inputs and outputs were for the conveyor. So I'll write here MATLAB conveyor so that I don't confuse them. And then I'll start to then write the variables for the control, and I will say control panel, or some may say visualization. In visualization, I have the start, stop, reset, and auto. So we know that those are switches, so I'm going to refer to start as S1. So these do not need to have addresses, because you can see they're not physically available on the station. So we're going to use the HMI to control them. So you can address them, or you can opt to not address them. When you don't address them, they become what we call flex or internal bits. If you give them addresses which matches the physical, then it will mean that they will control the physical onboard IOs of the PLC. Just to make it simple for us, we're not going to address them. So we're just going to say Boolean, and we can write a comment to say this is start button. And we have S2, which is also a Boolean, and this is a stop button. We have S3, which is also a Boolean. This is a automatic manual switch. We have S4, which is also a Boolean, which is a reset button. What I must really, before I forget, is to talk about the indicators. You see, it's called HMI for a reason, human machine interface. I need to be able to monitor and also to control the system. At this point in time, I can only control, but I don't know what state the machine is, which is why I need to bring in indicators. So indicators can be lights next to the switch. So I have a light next to the start, so I need to specify what colors these are. So frame, you can leave it white because we don't want it to have a frame. And when it's off, when the light is off, we can leave it at white. But when it's alarm state or when it's on, I'd like it to be green to show that I may press the start button. So we do the same thing for reset, so that it shows that the system is in a state that can be reset. Okay. So for these, we're going to add outputs for the control panel, because so far we've declared inputs. So these are inputs. And now we need to declare the outputs. And we typically call them P1, which is also a Boolean. We can say start illuminator. We have P2, which is also a Boolean. This is a reset indicator or reset illuminator. Okay, now we just need to attach these different variables. So because this is a light, we will go to color variable. And we are going to go to toggle color. So what toggles the color would be P1. So we start with the name of the PLC program where the variable is. In this case, this is PRG, PLC PRG dot. This is P1. And we know that we have said that it's P2. We have P2. The start button itself, it doesn't change color because we have illuminator light next to it. We instead will go to input configuration and we go to tap, because we want it to be momentary. It's a momentary switch. It does not remain on after you've pressed it. So that's why we go to tap. So this is S1. And we know that this is S2. This is S3. This we do it by, because this is a toggle switch, it's not a tap. This is a we go to variable. And then we will say PLC again, dot, this is S3. We link it to S3. And this is S4. So this we go to input configuration. Tap. Variable PLC dot S4. Okay, now we need to include this in our code. Where do they start? Now, this is where ladder becomes a problem, because to have something happening in a sequence with ladder, it's very difficult, especially when you have a sophisticated system, which I'll show later in the next course. So now you're gonna use lots of flags so that you can have set of conditions for the different lines. So this is a headache when it comes to ladder. So at this point, I'm going to leave out ladder and I'm going to switch to sequential function chart. Sequential function chart and structured text are the most common type of programming languages. Imagine your cell phone. Cell phone basically has ICs with integrated circuits. So those ICs are programmed using something called function chart. Function chart is very, very much like sequential function chart. They're very similar. All right, so now that we have declared our variables in terms of the visualization variables, we will have to code them as well. So first of all, we want the reset, which is going to be S4. So S4 is going to set an internal variable, which we can denote as L1. So this I'll save it as an internal variable. You can see it pops up there. So S4 will turn on L1. So here I'll use set reset. S4 is going to reset L1, while S1 is going to set L1. Excuse me for that. So we need to put in an input there. So start. So start is going to set L1 and so on, so that when you press start, L1 remains on, and we need to have it as condition together with optical and inductive. So that if I press S1, L1 becomes true, and if any of these sensors picks up something, M1 will turn on or K1 will turn on, depending on what that thing is, whether it's in the metallic part or workpiece at the beginning of the conveyor. Okay, so here we can have OR. So to do OR, we can have here, this is S2, so that we say, if I press stop, then all of these should turn off. Another way is, if I press reset, then this should turn off, and reset in any ways put everything back to initial position. But also, what is important is for us to illuminate the start, so that we can show that the system may be started. And system may illuminate when L1 is false. So if L1 is false, then we illuminate P1, so that it shows that the system may be started. But when the system is running, it must show that it may be reset. This is P2. But we must not forget automatic manual also. So automatic manual has to be a condition together with S1, so that the system must be on automatic and I must press the start. So this is going to be S3. I must put it on auto, obviously at first, and then I can then press start. I put the part, conveyor runs forward, part reaches the end of the conveyor turns off. I put a silver part, conveyor runs, they detect that it's metallic, it's sorted, it stops. Now let's see, what if I stop it while it's running? You can see that it does not turn off immediately, and this is because of the T off, which means that these should have been in front instead of here. They should be here, because T off will remain on even though the signal is 0. So putting them here will simply mean that it will cut the signal to the actuators, irrespective of whether the conditions are met. Okay, let us test it one more time. So at first I need to turn auto, start the system, put the part, press stop, voila. Let's see with the silver. Start, put a part, it's transported, stop. That's it. Thank you very much for staying tuned in. I hope that you've learned something today. Just to recap a little bit, we have looked at commissioning of hardware, where we connected the PLC with the hardware. We've looked at studying a program in ladder logic using codices. Then we've also looked at loading the program into the PLC and testing the program to see how it actually runs with the system. We've also looked at visualization, which covers the topics of SCADA and HMIs. Thank you very much. See you next time.